It's, all right, but the technological adaptations that we're seeing that need to be implemented, I guess, for dealing with the countermeasures that I've discussed, in particular encryption now, because you can't, RASCAT is a lot harder to deal with. We're seeing acquisition procedures change, right? The traditional, until actually very recently, most law enforcement departments would approach a running computer as if it were a problem, right? They would see a running computer and it would be like, oh, and then they'd have to pull the plug on it because, after all, you want to preserve the state of the disk. And that was the standard MO for police acquisition. That's obviously pulling the plug now is going to give you very little when there's an encrypted drive. So that for one has changed and is probably going to no longer be the case. Increasingly, running systems, the first step that's being used if you have interactive control is to run tools to screen for encryption. CERT makes some that are very effective at determining whether or not you have full disk encryption in place, whether or not there are encrypted volumes mounted, what's going on in the system. And when in doubt, increasingly also the norm is taking a live image of the computer disk, right? Grabbing memory, usually a full physical copy of memory. But that's if you have interactive control, right, which we don't always have. If you don't have interactive control, then it gets really interesting. One of the things that you have that the average attacker of a computer system would not have is physical access, right? You're in the room with the computer, by and large. If you're serving a search warrant, I hope you're in the room with the computer. So you've got physical access you can leverage. In the case, if you want to, and the computer's running, and you want to get, say, a memory dump, you can use FireWire, or plug in a PC card and use FireWire through it. That's thanks largely to the work of Max Dornsief and Adam Boileau, who've figured out a lot of neat stuff with that. You can also, if there's a network in the environment you're searching, you can harness the fact that very often internal networks have some higher trust level, and you can get on the network and harness that trusted status to perhaps escalate privileges. And finally, you're looking at exploiting vulnerabilities on the box, on your target system, and you're looking at services and applications that may be vulnerable. Sounds fairly natural, I'm sure, to many of the people in the room, but you've got to think, again, from the point of view of law enforcement and from the point of view in particular of courts and lawyers, that now they're going to have to figure out a way to introduce as evidence stuff that you hacked into a box to get, right? Like, wait a second, what did you do again? But you see where this is going, right? Because of these countermeasures and because of the change in the environment, increasingly gaining access to gain evidence is going to look a lot like the stuff that computer crimes are made of, breaking into computers. It's also going to require new skills. So acquisition team is going to become more specialized. Now, this probably isn't as, in and of itself, isn't as unusual as you'd think, right? When police discover a large safe in the corner of the room, it's locked and nobody's going to give them the combination, there's no problem calling a locksmith in, having him break into the safe. That's standard procedure, and it doesn't really harm evidentiary. I mean, that's been accepted nicely in courts. It's not a problem. But it is something they're going to have to think of now in terms of computer acquisition. And it's only going to probably get worse, right? It's just like the arms race in the broader security sphere. As the incentive, as investigators get more skilled at defeating these defenses, the defenses themselves will get stronger. So you need a little bit of flexibility. You need to be able to use very sort of ad hoc methods, adapt methods to what you see at the time, and some offensive skills. Now, these are definitely not qualities that are emphasized in the forensics community. The forensics community is built on doing things the exactly accepted way, the practiced way, the way that's been already succeeded in court when you've admitted evidence. And so it's a big and will be a wrenching transition to start incorporating these sorts of techniques into the acquisition process. All right, so what I'd like to do is run through a quick scenario just to demonstrate what this might look like. This scenario is actually based on a real-life case about a year old, again. It's just based on the case, so there will be some important differences. But this case, we've grabbed physical memory from this box. So we came in, there was let's just assume we've all entered a room. Assume you see there's a running computer, it's locked. You have a FireWire port, yay. You can grab access, you can grab physical memory from the system with FireWire. Discover that the system is full disk encryption, in this case, best crypt volume encryption. So you've got a disk image of an encrypted disk, right? You've got an image of memory. What do? What's next? Well, if you have memory, the good news is you have the key, right? You have the key that's used, that BestCrypt uses to encrypt the drive. It's somewhere in memory. It'll be in kernel pool memory, actually. And you can extract it and decrypt the drive. Yay! But you can do, perhaps, something a little more. Or you could have, we did a year ago. And that is, you can get something a little more valuable from memory. What's more valuable than the key to decrypt the drive? Any guesses? How about the passphrase? Why is the passphrase more valuable? Well, it tends to be used, passphrases tend to be reused, and if they're not reused, they tend to give you insight into how passphrases, how the other passphrases that are used might look, right? What they might look like. So a year ago, it was pretty much the case that every full disk encryption application was really good about cleansing memory from once you entered, if you entered a passphrase and it needed it to decrypt or to access the key material container, it would then scrub the passphrase from memory as soon as it was done using it. But until a year ago, most of the applications forgot one critical thing. So when you boot into a full disk encryption environment, you've got a pre-boot authentication phase, right? Sort of like roughly where your BIOS initialization screen it transitions right into this little environment where it asks you to enter a passphrase. When you enter the passphrase, you're still in that environment. And then control transitions to the operating system, and off you go. What the full disk encryption vendors didn't realize was that there's a BIOS keyboard buffer that none of them wanted or realized to clear. That's roughly, it starts at hex 41E if you take a linear look at physical memory. It'll hold 16 keystrokes. Actually, what it holds is the ASCII keystroke and then the scan code for the key that was pressed on the keyboard interspersed. And it will wrap. It's a ring buffer. So there's a pointer to the head and tail. This has actually been known. So can you see? You can probably see in there, right? What was typed here. This is. You have to sort of skip every other character because every other one is a scan code, but it says, "Hi there, HITB!" exclamation point. Right? So this has been known for about 10 years, right? There have been disclosures and grumblings on lists about how initially it was mainly a concern for the BIOS password, right? Not full disk encryption, more modern. But it's been rediscovered again and again. In 2005, as it directly pertains to full disk encryption packages, there was a couple of vulnerability reports in 2005 I've cited there. There's one just earlier than this year, and the one that was reported this year named a bunch of vendors, and as a result, I think it's gotten a lot more attention. So the bad news is, remember I was talking about the arms race? Well, bad news for investigators is, a year ago, you could recover the passphrase from that area of memory for practically every full disk encryption application. Now, you can do it for, if you're lucky, maybe there's half of them that do it. TrueCrypt, when it launched its full disk encryption package, was very careful right from the start to scrub that space. Bestcrypt has started doing so as of a few weeks ago when it released version 2. Latest PGP does reportedly. Pretty soon this hole is going to be closed completely and we'll have to move on to different methods. But let's go back to the scenario. So we're back in our scenario. What happens if we've got a passphrase that we've extracted from memory, from this BIOS keyboard buffer, that's longer than the 15 characters that can be stored there? Well, I mean, it's a 16-character buffer, but the last one's always going to be returned. So it's 15 characters, really. And in fact, a year ago we did. This was what you see there was what we recovered from the buffer. E-A difference, exclamation point. That was the last component of this guy's passphrase. Well, that could be B a difference, C a difference, R a difference, I am a difference. No, it wouldn't be I am, but anyway. Make a difference, take a difference, fake a difference, fake a difference. There's a bunch of stuff. I mean, what we ended up doing is having to create a very lengthy list of possibilities, scripting it out. But then you've got another problem. There are no commercial password crackers that handle Bestcrypt volume encryption, right? So what do? Well, you can actually make one yourself, but when you do it, you've got to keep a few things in mind. One of the most important ones, and this is one of the ones that's the hardest to get around, is that usually it's time sensitive, because if we're talking about material that was seized during a search, there may be a very big difference between what crimes can be charged, the individual can be charged with, or the group can be charged with, if you recover this material than if you don't. Right? So it makes a fairly large difference, even very early on, because you have to be charged quite early. And the other thing you have to keep in mind is that whatever we do, it has to be something that you can demonstrate in a court of law provides forensic quality evidence. That's not that easy, but again, it's not that hard, but again, it's something you have to keep in mind. So for this, what we'll do first is we'll use LiveView, which is the tool I mentioned, or the tool I mentioned earlier that's publicly available. It's available via SourceForge. And we'll take our disk image, the image of that encrypted drive, which is just a bitstream copy of the content of the encrypted drive as one big file. And we'll virtualize it. We'll create a VM around it. So that's what LiveView does. And it does it very well, actually. And if you've got a unencrypted Windows machine, LiveView will do a lot of massaging to the machine, set up the hardware for it so that it will actually boot up nicely within the VM environment. Has anybody in the room seen LiveView before? It's widely available. The URL's there. There's a law enforcement version that isn't widely available, but c'est la vie. So what we do here is basically just use it to create a VM that we can use based on that encrypted drive. And then, once we've done that, once we've done that, we've got so the VM will let us play around with that disk. And the one thing that LiveView does really nicely is it will create, it uses VMware's disk snapshotting feature, which means that if you've got a working copy of the evidence that you don't want to keep copying again and mess up, LiveView will create what's effectively a diff file, a separate file to which all the changes to that disk are going to get written. And so that gives you the ability to use, a nice working image that you don't want to change